Hi students, we are going to continue with Module 5, Part 2 about universal gate. The universal property of NAND and NOR gates. What does universal property means? It means that our NAND and NOR gates are special gates which can actually represent all the other basic gates. The NAND and NOR gate will be converted and perform the function of our basic gates of AND, OR, NOT. Or even NAND can represent NOR and NOR also can represent NAND. That is why we call NAND and NOR universal gates. So why do we need this universal gate? I usually give you examples, in previous module. Our objective is to try to maximize profit for our employer, for our bosses, by trying to minimize the circuit using the least number of gates. However, the number of gates is not the only criteria. Let me give you an example. So your boss gives you a circuit drawing. So there are two of you, me and the other person B, needs to come up with the best solution. So I draw the same circuit with only 5 gates. Just 5 gates produce the same function. The other engineer come up with the same output, however, with 20 gates. But these 20 gates are from the same gate only, NAND gate. So 20 NAND gates compared to my circuit, 5 different gates. 1 AND, 1 OR, 1 NOT, 1 NAND, 1 NOR. So which one do you think your boss will choose? In this case, your boss, I think, will choose the other person, because even though it is 20 gates, but they are from the same gate, NAND. It's actually a good thing to implement our final circuit using only a single type of gate. What are the advantages? Why your boss choose the other design? Because then you only have to stock one type of gate instead of saving 5 different kind of gates. So different kind of gates, 5 different schematic diagram, 5 different understanding. You only need one NAND gate. And when we buy the same gate a lot, of course it is cheaper, isn't it? And also, the other advantage is we can reuse the extra unused gates to implement other gates. Only one gate to implement all other circuit. So the 2 gates that we can use, that is NAND and NOR. Usually, SOAP is implemented using NAND and OR logic. SOAP, NAND, post is NOR. Very easy to remember. Let us look now, how can we convert all our basic gates into NAND gate. We start with NAND gate, Later, we'll see NOR gate. So to represent a NOT, we only need one NAND gate. However, NAND usually has 2 wires, right? 2 input wire. So to make this NAND gate, all we have to do is to twist the 2 wires together. That means only one input A. Which is, okay, look. So one input is A. The other input is A. A dot A is equals to A, and then we have the bubble, so now it becomes A bar, which is a NOT gate. Easy, isn't it? Okay, let's look at how to get AND gate from NAND gate. Okay. For AND gate, yeah, you need 2. Okay, I always consider AND and NAND to become siblings. Yeah, they are sisters. NAND and AND, they are sisters. So you only need 2. You will know why I call the sisters when I'll introduce you to NOR. Yeah. So AND, the sister is NAND. So you only need 2 NAND gate. The only thing you need to remember is how we arrange the gates. I will teach you how to memorize this 1, 2, 3, the number of gates to represent in a table later after this. But you must know if 2 gates, how to draw the representation. So for 2 gates, yeah, you start with 1 normal NAND gate. So 1 normal NAND gate is AB bar. And how to get how to get N is AB. That means we want to cancel out the bar. So actually this is, okay, yeah, there is another bar here. So our AB bar, we put not on that. So now we can cancel our bar. That's how we end up with NAND gate. So for N, you need 2 NAND gate. So if our AND gate is a sister to our NAND, then our OR gate is the cousin. So if our sisters, yeah, use 2 gates, our cousin OR will use 3 gates because N and OR are different, right? So you need 3 gates of NAND to make up to get OR gate 3. And how do we arrange it? Of course, yeah, 2 AND gate. You start with 2 NAND gate, and then you end with 1 NAND gate. Yeah, it's very obvious. Obviously, if you try to imagine you start with 1 NAND and then you cabang to 2 NAND gate, doesn't work. Let's prove it. So the first NAND gate, yeah, A bar. So it means you twist the input A, and then you twist the input B, so you get A bar, B bar, and then you put another long bar above it. Please De Morgan this. Alright, you will end up with AB bar. But let me just write it here. Okay, so dot becomes plus, long bar becomes short bar, you get A plus B. Proven, this is an OR gate and you need 3 NAND gate. We don't need NAND to represent NAND because it is already NAND. That means we need to represent NOR because NOT is 1, N is 2. OR is 3. So now, NAND, you need 4 NOR gate, yeah? Sorry, NOR, you need 4 NAND gate. And the drawing, very easy. What is 3? 3 is OR. Yeah, 3 is OR. So this is OR. Yeah, this is OR. And how do we make it to become NOR? We just put NOT bar. So now this is a NOR gate which needs 4 NAND gate. As promised, I'll teach you now how to actually memorize how many gates used for all the basic gate. Alright, for our NAND gate, we start with, of course, only one NOT gate. Sorry, only one NAND gate to produce NOT. And NAND is sister, so you need 2. Or is the cousin, you need 3. NAND, obviously, you don't need any conversion. And NOR is 4. I haven't teach you NOR, but it is very easy. The difference is you change the NAND gate to NOR gate. To represent NOT with NOR, you need 1 NOR gate. Okay, now, how about AND? 2 NOR gates. This is where the siblings and the cousin come in. AND and NOR is cousin. They are not the same. Okay? OR and NOR is sibling. They are brothers. So OR and NOR needs 2. And because OR needs 2 NOR, and we need 3 NOR. And how about NAND? NAND and NOR? 4. Obviously, you don't need NOR. This is the easiest way for you to memorize how many gates of NAND and NOR needed to represent the basic gates and also the other universal gate. This is the notes of how to do the conversion. Let's look at this example, exercise 5.2. Use NAND gates to implement each expression. Alright, how do we do this? How do we do the how do we draw it with NAND gates? There are a few ways to do it. In this part, I'm going to show you one way. How to do it? First, you draw with the basic gates first. So A bar and OR plus B. Alright. Next, each basic gate, convert it. Based on the table that I just draw for you, convert it with NAND gate. So, how many gate for OR? 1. Yeah, you need 1. And OR gate is cousin with NAND, so you need 3. Okay, so convert it. 1, G1 for NOT. And for OR, you need 3 gates, yeah? 1, 2, 3. Okay. So you convert it. However, this is not the final answer. Why? Yeah, just like our class just now. Because this is not simplified yet. Okay, look. Which one? What you need to find is if there are 2 gates in sequence, one after the other. You cannot have anything in between. So one gate and the next gate, similar gates. Then you can cancel. Or how about this? Okay. Look at this. You start with A. Yeah, you start with A. And then you invert it to A bar. And you invert it again to A. Here. So why do we actually need G1 and G2 if we can straight away start from here to get A? And if you look closely, this is one NOT gate, which is NAND gate with 1 input. This is right after that is the same NAND gate with 1 input. They are the same you can cancel them. Please. That's why you end up with either. So your final answer is actually this. So which one is better? The one with the basic gate or the one with NAND gate? Obviously, okay, both use 2 gates, but the basic gates have 2 different gates, not an or. Your boss will tell you, please use the one with the universal gate because same number of gates, but one type of gate, which is NAND. So you can try also with this. So first thing is convert it. 1 gate, 2 gates, you got it. And no cancellation needed. Okay. Let me just give you a warning. Quite a number of your seniors make the mistake of trying to cancel this because they say one after the other NAND gate. They are not the same. Why? Look at this. This is 1 input gate. This is 2 input gate. They are not the same. Therefore, please do not cancel. Yeah, be careful. Another example. So how many gates needed here? 2 NAND gate, 2 NAND gate, 3 NAND gate. We should have 7 NAND gate. Our first step, conversion. So there's 2, there's another 2, there's another 3. So total 7. What is the next step? Find those that are in sequence and same gate, same NOT gate. So in our class just now, I think it was, someone said G1 and G5 cannot. G1 and G5 cannot because you have G2 in the middle. And another person said G1 and G3. Of course cannot, yeah? They have no connection. So actually where? G2 and G5. Look, 1, 1. And G4 and G6. So you actually ended up with 3 NAND gate. And what is this? This is AND OR logic. So with AND OR logic, remember in the first, in the beginning of the video, I said AND OR logic, we use SOAP. Yeah, SOAP. And actually NAND. I said NAND use SOAP. And SOAP is AND OR logic. So this is AND OR logic, which is SOAP. And SOAP, you just convert it. Yeah. So with SOAP equation, with AND OR logic, you just need to convert this, the 3 basic gates, the 2 NAND and the 2 OR, all to NAND gate. So 2 AND, 1 OR, AND OR logic, SOAP expression becomes 3 NAND gate. Yeah, but if you are not sure, you can always do conversion first, cancel out. Once you know about NAND gate, I've taught you the fundamental, I've given you the table. NOR gate is the same except change the gate from NAND to NOR. And be careful, now for 2 NOR gate, it is for OR. It is for OR. Because OR and NOR is siblings, you use 2. OR and N is cousins, you use 3. And then for to represent NAND with NOR, you use 4. Same fundamental. Same way to implement expression. Draw the basic gate. Change each gate into NOR. Look for NOT gate if you can cancel them out. This one, no. Yeah, and this one, yes, you can cancel this and this. You end up. So you end up with this circuit. Yeah, very easy. So that's it for universal gate. In conclusion, NAND and NOR is called universal gate because you can use both gates to represent all the basic gate and also the other universal. So NAND and NOR can represent NOT, can represent AND, can represent OR, and also NAND or NOR. So you don't have to use different types of gates to draw your drawing to produce your circuit, but only use one type of gate, which is NAND or NOR. Yeah? Most of the time, yes, you will use slightly more number. Yeah? It's one type, but maybe extra gate. But as you have seen in the examples, there are times when your two basic gates can be drawn with two universal gates. Then obviously, yeah, we use universal gate. We will continue with part 3 after this. Bye!